let's talk about alcohol oxidation. So we now know a couple different ways to make alcohols from alkenes, for instance. And we know a couple different reactions that start with carbonyl compounds, and we'll learn more in the future. So now we want to connect these two things. I want to be able to oxidize this CO bond here to a CO double bond. Okay, so the best way, there are many, many ways to do this. So there's literally a book in our library that's that thick that is essentially all ways to do this kind of reaction. Why does there need to be so many ways? Well, in addition to effectiveness and high yield, we're also always trying to think about waste and toxicity and being able to make everything catalytic, so we use less precious material. But I'm going to teach the old school way first. So the old school way to do this would be to use something called the Jones reagent. So the Jones reagent contains chromium. It's chromium trioxide with strong acid, sulfuric acid, in water and acetone as the co-solvents. So this is usually made up ahead of time. We have some in our lab. It's this thick, red, viscous, death-looking liquid. It's red because chromium-6 is red. Chromium-6 is pretty nasty stuff. So if you've ever seen the movie Aaron Brockovich, which if you haven't seen the movie Aaron Brockovich, you should, because Julie Roberts is a delight in Aaron Brockovich. It's a good movie. I think it won the Oscar. But regardless, a big plot point of that movie is that chromium-6 is leaching into the groundwater and causing massive health effects. So at any rate, how do we think about the reactivity here? Well, it is inorganic chemistry, but we can kind of cheat and think of it like organic reactivity. So if we think about chromium trioxide as something like this, almost like has 3 double bonds to oxygen, and that in strong acid will add an acid proton, then we can kind of squint and say, okay, that looks like C that I would usually attack with some nucleophile. It's just CR, right? What's an R? Nothing. So we're going to have this lone pair as a nucleophile. Here's my electrophile. Again, I'm making my electrophile super electrophilic. So what does that give me? What it gives me might look something like this. Sometimes this is called a chromate ester. Now, this is a really unstable thing, and this is where the reduction comes in. So our arrow pushing is going to be in a 5-membered ring like this. And notice that chromium's giving up electrons and getting electrons on the back end. What does that give us? What it gives us is this reduced chromium and our carbonyl compound, right? I made this double bond. And again, this is reduced because we would call this chromium-4 coming from chromium-6. So the chromium is reduced as my carbon is oxidized. Pros and cons to using the Jones reagent. You don't need to memorize what Jones reagent is. I'll give you the chromium trioxide. Pro, it works. It's an old-fashioned reaction that has stayed in practice for a reason. It is effective. Con, it has really, really toxic chromium in it. And not just a little bit either, a stoichiometric amount, a lot of it. This is not catalytic at all. Pro, there's a built-in color change because chromium-6 is red and chromium-4 is green. When your reaction turns green, you're all the way oxidized. Con, really, really, really strong acid. If we're doing something kind of sensitive, trying to make a very complicated natural product or a drug that might be really sensitive to acid conditions, this is probably going to wreck it. Here's another con. So I drew this particular one for a reason. So this is a secondary alcohol that is oxidized to a ketone. We obviously couldn't oxidize a tertiary because I wouldn't have a hydrogen here if it was a tertiary, so there would be no way to oxidize a tertiary alcohol. The secondary alcohol is oxidized by Jones reagent in pretty good yield to a ketone. Now, what about a primary alcohol? You might hope that this would oxidize an alcohol directly to an aldehyde, but it turns out it won't. So if I treat a primary alcohol with Jones reagent, I actually get a carboxylic acid. Why doesn't the Jones reaction work for primary alcohols? It does work. It works all too well. What happens is, first we oxidize to the aldehyde, but if we're in water, especially with acid catalysis, this aldehyde is going to have water add to it to form a hydrate. We're going to talk about this particular equilibrium in like 3 or 4 videos from now, maybe fewer. Anyways, this is an equilibrium, and even though this is only a tiny part of that equilibrium, every time the Jones reagent catches it as a hydrate, it's able to say, oh, OH, an H there, I got this. And so it's going to oxidize this up to the double bond. So the Jones reaction, there's really no way to stop it at the aldehyde. We're always going to get the carboxylic acid. So if that's what you wanted, cool, do that. But if it's not what you wanted, we're going to have to think of a better way to get to the aldehyde. Here's a better way. We can use something called pyridinium chlorochromate. Nobody remembers that. People remember it as PCC. This is what PCC looks like. It's essentially chromic acid with HCl instead of sulfuric acid that's been buffered with this base. Pyridine is an amine base. And so it's just kind of like a less acidic Jones reaction or reagent. So it's less acidic. That means that A is probably safer for our molecule, but also B, it's going to slow the rate of hydrate formation. And so we're not going to have that equilibrium quite as much as we did before. And because we don't have hydrate, we don't have overoxidation to the carboxylic acid that goes through the hydrate. So PCC is a pretty good way to take a primary alcohol and turn it into an aldehyde. It will also take a secondary alcohol to a ketone as well. So basically PCC can do both of these things. Now, take a second, maybe even pause, and think about one pro and one con of using PCC. Okay, so the pro is obviously what I just said. It's less acidic than the Jones reagent, and it will let us stop at the aldehyde. The con is that I'm still using stoichiometric chromium. That is bad, right? Aaron Brockovich. I told you about Aaron Brockovich before, and yet we still have chromium here, right? So A, this might be morally defensible on a very small scale, maybe, but on a large scale, especially on a plant scale, there is no way that we would ever use chromium as that. Now, why do I teach this if it's not the modern way? Well, one, these are the oxidizing agents that are probably on your MCAT and your standardized tests. And B, I think that this is a good first step into how a mechanism for an inorganic oxidation might look. But in the present day, these are probably not the first oxidation reagents that you might reach for, except if you're trying to really push a primary alcohol all the way to a carboxylic acid. In that case, you might want to reach for the Jones reagent. Again, there is literally a big library book filled with methods with which to do this. But I just want to take 30 seconds to talk about to at least mention probably the 3 most important oxidation methods to the modern organic chemist. So I mention this because you're going to be doing a little bit of literature research and looking at ways that people make drugs and other compounds. And so you might run into this modern oxidation. So I just wanted to show it to you here. Better ways to oxidize alcohols up to aldehydes without using stoichiometric chromium-6. All right? Probably the best and greenest way to do this is just bleach and acid. So sodium hypochlorite, if we add some acid, it becomes HOCl, hypochlorous acid. And that's a pretty good oxidant for this purpose. We usually do this in a lab where we take an alcohol and treat it with Clorox bleach right out of the Clorox bottle and acid and get an alcohol in get a ketone in pretty good yield. Another way that has kind of taken over the modern synthetic literature is called Des-Martin periodinane. It looks like period, but it's got iodine, so it's periodinane, sometimes abbreviated DMP. DMP is this mamma jamma. So check it out. Iodine with 5 bonds and a lone pair. Iodine scoffs at your octet rule. Ha! It says, if it could. It can't. It doesn't have a mouth or intention. But you can tell that this iodine is very, very oxidized, and it's relatively easily reduced. So DMP is a very gentle, very nice way to oxidize. Lots of pros. Very high yielding, easy to use. Cons, pretty expensive, and just a wee bit explosive. So we have to watch out for that. And another really good kind of older school way is called the Swern oxidation. Uses DMSO. Your oxygen is going to come from this DMSO. It's activated by this acyl chloride called oxalyl chloride and a little bit of base. So 3 modern methods. You don't really need to know these, but if you see them, I hope this kind of trips your brain. Oh, this is an oxidation step. So bleach, Des-Martin periodinane, and Swern oxidation. Again, we're talking about this because we're starting to build our synthetic web. We know ways to make alcohols. We're going to learn more ways to make alcohols very soon. We know how to do reactions with CO double bonds. We're going to learn more of those. Being able to oxidize alcohols is a way to connect those 2 bodies of knowledge and kind of connect our 2 webs, right? Now, how do we get from aldehydes back to primary alcohols? We're going to talk about that very soon too.